Okay, so let's continue our lecture on the properties of Riemann integrals. We left off we left off with this theorem here. This theorem says that the set of integrable functions is actually a vector space. So it's closed under adding and scalar multiplication. So here's the way you write this. If f and g are integrable on AB and c is a scalar, some fixed number in R, fixed constant, then c times f, that's a brand new function from AB to R. C times f and f plus g are both integrable on AB as well. And I'll say just as a side note, we won't prove it here, but also f times g is going to be Riemann integrable, and the max there, the max of f and g. So if you look at a function, it's like, say this is f and then g is here, right? So if you wanted to look at the function max of fg, where at a point, say x, the max of fg is going to be whichever one is bigger, right? The max of f of x and g of x. For the picture that I've drawn here, the max of fg would be the function that's this, right? So it's a brand new function that's the maximum of f and g at each point. That would also be Riemann integrable. And also min, right? So if you have integrable functions, all sorts of combinations of functions will be integrable based on that. Okay, so let's go ahead and just look at the proof. I'm not going to go through the full proof. The full proof is in our textbook on page 282. I'll just walk you through how to show that C times F is Riemann integrable whenever F is Riemann integrable and C is a real number. Okay, so this actually is two parts. So first of all, not only is CF Riemann integrable, but the integral of C times F is C times the integral of F, right? So that's kind of important there. So we have like two results. First is to show that CF is Riemann integrable, and the second result is to show that its integral is equal to this number here. Okay, so let's just get started here. And so we'll say we're going to do the proof. In order to do the proof, you're going to consider three cases for C. So this will be a proof by cases. The cases will depend on if C is greater than 0, C is equal to -1, and then if C is less than 0. Now, there's one remaining possibility, which is that C is equal to 0. And the case where C is equal to 0 is trivial, because if C is equal to 0, then we are talking about the 0 function. And all of our upper sums and lower sums will be equal to 0. So the sup of our lower sums will be 0. The inf of our upper sums will be 0. Those will be equal to each other. So our function will be Riemann integrable, and the integral will be 0 times whatever that number is, right? So this case is trivial. And then you might be wondering, hey, why are we looking at C equals -1 as a special case? Isn't that covered by C less than 0? And it's true. If C is equal to -1, then C is certainly less than 0. But for the flow of the proof, what we'll do is show that if C is positive, our claim is true, right? And then our claim is true for -1, right? And then we'll say if C is negative, then negative C is positive, right? And so we'll have that -1 times C, okay? So that's why we separate C equals -1 as a special case. So let's start with case 1. Case 1 is C is positive. So if C is positive, then we're basically going to look at, let's look at a partition. So fix a partition P, so it'll be some T naught less than T1 less than Tn. And remember, T sub n will be B, T naught is going to be A. And let's consider our upper sums, okay? So then, if we want the upper sum of C times F with respect to P, that would be the sum of, now I need the sups of CF on each subinterval. So it'll be T K minus 1 to T sub K times the length of that subinterval. Okay. K starting at 1 and stopping at N. And now the sup of C times F is just going to be C times the sup of F because C is positive, right? So this will be equal to C times the sup of F. Okay. And now notice this is going to be C times the upper sum of F with respect to P, because we can just take this C and bring it out. And then what's left is the upper sum of F with respect to P. So that's going to tell us that the nth of these upper sums is the nth of the set of C times the upper sums. And again, because C is positive, we can bring it out front, right? Which is equal to C times the nth of the upper sums of F. So this, which is our upper integral, is going to be our upper integral of CF is going to be C times the upper integral of F, okay? And the same argument would apply for the lower sums. And again, all of this is okay because C is positive. So copy. Let's add a page here. So if we were to do the same analysis for the lower sums, we would say, what's going on with the lower sum of CF with respect to P? Well, it's the sum of those areas using the nth, right? But the nth of C times F will be C times the nth of F. So we'll get this. Now we're concerned with the sup of the lower estimates, okay? That'll be the sup of these lower estimates, and that's just going to be C times the sup of these lower estimates, which is your lower integral, okay? So we have that the lower integral of CF is C times the lower integral of F, but the lower integral of F is the same as the upper integral of F since F is Riemann integrable. That means that the lower integral and the upper integral are equal. And then we proved in the first part that, so this is going to be equal to, oh, my little pen is down. So give me a moment here. So this is going to be equal to C times the upper integral. But remember, we just proved that C times the upper integral of F is the upper integral of C times F. And this is true when C is bigger than 0, okay? So CF will be Riemann integrable as desired. And the integral of CF is going to be c times the integral of f, because the integral of cf, that's going to be either the lower integral or the upper integral when those are equal, and that'll be equal to c times the lower integral of f, c times the upper integral of f. So we get the equality that we desire. Okay. Now I'm not going to run through the case for when c is equal to -1, but it's relatively short. We're basically using the properties of soups and infs, of sets that we proved all the way back in the beginning of the semester, right? Remember we had we proved some things like, what's the soup of minus a, right? If a is a subset of R, the soup of minus a is equal to, let's see, okay, I always have to draw a picture. And the way I imagine it is, say here's a, right? And now here's the soup of a. And if I flip this over to look at minus a would be back here, right? So like this point here would be sent over here. And my soup would be sent here. And so my soup of minus a is going to be minus the nth of a, right? Because that's the nth of a. So an easy way to remember this is to just draw a picture which generalizes the situation. So if a is some subset of positive numbers, then when you flip them, the numbers are going to be negative, and you can visually see what happens to the soup of negative a, right? So soup of negative a is going to be minus the nth of a, and you use these little equations like this to look at the lower sums and the upper sums when c is equal to -1. Okay, so that's essentially what you're doing for the case when c equals -1. And then lastly, if you have a negative number c, you just say, well, a negative number, if c is less than 0, then minus c is bigger than 0. So you can apply this and this to compute the integral. Okay, all right. So, and then the other one that I didn't go over, but I leave it to you to read, is showing the f and g are Riemann integrable, and the integral of f plus g will be the integral of f plus the integral of g, right? And so the key fact there is, okay, if you're looking at your nths, the nth of f plus g is bigger than the nth of f plus the nth of g, and, set computations like that. Okay. So the next theorem here is a way to compare functions or integrals of functions that are ordered. So our hypothesis is that f is less than or equal to g. They're both Riemann integrable. The claim is that the integral of f is less than or equal to the integral of g. So let's look at that one first. And I've kind of sketched it out here for you. I wrote it here. But basically what we're doing is looking at pictures. Suppose, right, so we said f is less than or equal to g. Okay, so that means that g is higher and f is lower. Okay, so f is less than or equal to g. F and g are both Riemann integrable. That's hypothesis. And then the claim is that the integral of f is less than or equal to the integral of g. Okay? And so for a sketch of the proof, here's what we're going to say. We're going to say that the integral of f is less than or equal to the integral of g if and only if the integral of f minus g is less than or equal to 0, right? And that's the same thing we can just say if and only if the integral of g minus f is bigger than or equal to 0. So all I did was subtract this integral from both sides, right? So now my left-hand side is equal to 0. And on the right-hand side, I have Right-hand side, I'll have the integral of g minus the integral of f. But remember, by our last result, right, the theorem that we just proved, this implies that we're looking at the integral of g minus f, right? Because if f and g are both integrable, then g minus f is also integrable, and its integral is equal to the integral of g minus the integral of f, okay? So, by the last theorem, it suffices to show that the integral of g minus f is bigger than or equal to 0 whenever g minus f is bigger than or equal to 0. And so, and g minus f is Riemann integrable. Okay, so here's what we do. Instead of working with g minus f, we just say, hey, let's call g minus f, let's just call it h. It'll make our notation easier. So now we're supposed to prove that if h is a function that's bigger than or equal to 0 and h is Riemann integrable, then the integral of h is always going to be bigger than or equal to 0. Okay? So say h is bigger than or equal to 0, h is Riemann integrable. We want to show that the integral of h is bigger than or equal to 0. But that's going to be true because the integral of h is going to be equal to the sup of the lower sums. Right? It's also equal to the nth of the upper sums. But we don't really care about that part. What we care about is that the integral of h is the sup, it's the biggest, right? It's the supremum of the underestimates. And since h is bigger than or equal to 0, that means that the infimum of h over any subinterval, right, tk minus 1 to tk, is going to be bigger than or equal to 0, right? So if my function is bigger than or equal to 0, if all my values are bigger than or equal to 0, then the infimum has to be bigger than or equal to 0 because 0 is a lower bound, right? And the infimum has to be bigger than or equal to any lower bound. So this is going to be this implies that each m of h tk minus 1 tk for any partition, right, is bigger than or equal to 0. So if I take that and multiply it by the length of the subinterval, that's going to be bigger than or equal to 0, right? And then if I add those up, I'm going to get something that's bigger than or equal to 0, right? But this left-hand side is just the lower sum of h with respect to a partition P, right? So back here, our integral is the sup of these lower sums, but the lower sums are all bigger than or equal to 0. So if here's 0, all our lower sums have to be bigger than or equal to 0. That means that the sup of them also has to be bigger than or equal to 0, right? The sup can't be over here because if the sup is less than 0, it's not going to be an upper bound. So the sup has to be bigger than or equal to 0. So the integral of h has to be bigger than or equal to 0. So hopefully that kind of makes sense. We're basically saying we're trying to rigorously prove that if the graph of your function is above the x-axis, what we're trying to prove rigorously is this. If you have a graph of a function that's above the x-axis, the graph is above the x-axis, then any upper sums and any lower sums are going to be bigger than or equal to 0. So the integral has to be bigger than or equal to 0. Okay? So that would be the proof here. And this is a summary I gave. I said consider h equal to g minus f. Then h is integrable by the last theorem that we proved, right? And h is bigger than or equal to 0 by the hypothesis. So for each partition P, that lower sum of h with respect to P is bigger than or equal to 0. Okay? So that means that the integral of h, which is the lower integral, which is the soup of all of these, has to be bigger than or equal to 0, and the result follows. Okay? And then for the second one here, suppose g is continuous, non-negative, then if the integral of g is equal to 0, then g is identically equal to 0. Let's prove that. This one is kind of cute. So for hypothesis, we're saying suppose g is Riemann integrable, g is bigger than or equal to 0, and the integral of g is equal to 0, right? The claim is that g has to identically be equal to 0. Okay, so g, of course, is defined on sum a, b to r. So what we're saying is if you have a function that is continuous, you have a function that's continuous, and it's bigger than or equal to 0, and its integral is equal to 0, then that function has to be the 0 function. And so the proof, I'll do the sketch of the proof. And what we do is do a proof by contradiction. We say, suppose not. We're contradicting g identically being equal to 0. That means there exists some x naught in our domain where g of x naught is strictly bigger than 0. Okay, so think of a picture. Here's a picture here. So here's A, here's B. And we're saying suppose G is not identically 0, right? That means that there's some point x naught where, well, that was a horrible, horrible drawing. Let me try again. Okay, suppose G is not identically 0, then there's some point x naught where G is bigger than 0. Now, so this is, say, G of x naught. And G of x naught is bigger than 0. Now, what does it mean to be continuous? It means for every epsilon, there is a delta. I'm going to let my epsilon be half of G of x naught. So now, this is my epsilon ball centered at x naught. For every epsilon, there's a delta where points within delta are mapped within epsilon, right? So what's going to happen is there exists for delta, for epsilon equals g of x naught over 2, which is positive, there exists a delta greater than 0 such that when x is within delta units of x naught, f of x is bigger than, g of x is bigger than g of x naught over 2, right? And smaller than g of x, 3 of g of x naught over 2. So here's the idea. So we'll have g of x naught over 2, 3 of g of x naught over 2. That's just based on my epsilon that I chose. So I now have some interval here where the values have to be at least this big. So whenever I am computing my lower sums, my lower sums have to, let's see here. So each lower sum of G with respect to any partition P must have, must be at least as big as 2 delta times G of X naught over 2, right? So even if G is 0 all the way here and then suddenly skips to here or something like that and then goes back to being 0, regardless of how my partition is defined, there's going to be the interval, the subinterval or the subintervals that include this little delta interval. Their inf has to be bigger than or equal to G of X naught over 2, right? So my lower sum, even if the area of all the other rectangles is 0, I'm going to have some little part that has a lower sum that's at least G of X naught over 2 times 2 delta. Okay, in other words, delta times G of X naught. So then for each partition P, the lower integral, the lower sum of G with respect to P is bigger than or equal to G of X naught times delta. Okay, so that means that the soup of all of these lower sums has to be at least as big as this, right? So my lower integral of G, which is the soup of all my lower sums, has to be bigger than or equal to G of X naught times delta, but that's bigger than 0, right? And this is my integral. My pen ran out again. So my integral of G, which is the same as my lower integral, right? Because your integrable, if and only if your lower integral and your upper integral are equal. So my integral, which is the same as my lower integral, which is the same as the soup of my lower estimates, has to be at least G of X naught times delta, and that's bigger than 0. So my integral has to be strictly bigger than 0. This is a contradiction to the hypothesis that the integral of G is equal to 0, right? So that is how you prove, this part 2. So I said proof by contradiction, use the fact that G is continuous to get an interval. This is that X naught minus delta to X naught plus delta that I was talking about in the proof, on which G is bigger than or equal to alpha over 2. So the alpha that I used was the G of X naught, okay? Then the integral of G will be bigger than or equal to, the integral of G on AB is going to be bigger than or equal to the integral just on that subinterval, right? Which will be bigger than or equal to the length times the minimum or the infimum. That's bigger than 0, which is supposed to be equal to the integral. So you get a contradiction because you're saying this number is bigger than itself. Contradiction. Okay? All right. And the main theorem here that we have is we're proving that f is integrable. If f is integrable, then the absolute value of f is going to be integrable as well. So for this proof, let's go through hypothesis. Hypothesis is that f is integrable. the claim is that the absolute value of f is integrable, and we have this estimate. Okay? So let's go ahead and write this up. So for hypothesis, f is integrable. The claim is that the absolute value of f is Riemann integrable, and the integral of f, the absolute value of it, is less than or equal to the integral of the absolute value of f. Okay? So for the proof, we have 2 steps. First, let us show, the first thing we want to do is show that the absolute value of f is integrable. Now, let's see here, step 1, show that the absolute value of f is integrable. And then step 2, then we'll say, now this is once we know that the absolute value of f is integrable, then f is always going to be less than or equal to the absolute value of f, right? And that implies that the absolute, that the integral of f is less than or equal to the integral of the absolute value of f. So since f is Riemann integrable and the absolute value of f is Riemann integrable, we can apply the last theorem. Because remember, the last theorem said if f is less than or equal to g and they're both Riemann integrable, then the integral of f is less than or equal to the integral of g, right? So that's what we're using to conclude that f is less than or equal to that, and f are both Riemann integrable. That implies that the integral of f is less than or equal to the integral of the absolute value of f. Similarly, f is bigger than minus the absolute value of f, right? Because f is going to be in between that its absolute value and minus its absolute value, right? So we'll have the minus is less than or equal to f if absolute value of f is Riemann integrable, then if the absolute value of f is Riemann integrable, then multiplying it by scalar, in other words, negative, has to also be Riemann integrable. And so we can again apply the theorem to say that the integral of minus absolute value of f is going to be less than or equal to the integral of f. But now we can use our theorem that we first proved today and say, well, the integral of minus f is the same as minus the integral of the absolute value of f, right? So we'll have that the integral of f on the one hand is less than or equal to the integral of the absolute value of f. And on the other hand, it is bigger than or equal to minus the absolute value of the integral of f. This means the absolute value of the integral of f is less than or equal to the integral of the absolute value of f. Okay? So all we need to do is show that the absolute value of f is Riemann integrable. And to show that the absolute value of f is Riemann integrable, we're going to use this fact here, which is comparing the sup and the inf of the absolute value versus the sup and the inf over the function. So just to imagine why this would be true, suppose you have a function. So I'm going to draw f in green, right? So say here's f. Now, if I draw the absolute value of, sorry, I drew f in black. I'm going to draw the absolute value of f in green. Or perhaps green isn't a good color because it's not going to show up. I'm going to do it in pink. So I use the positive values if f is bigger than or equal to 0. Okay? And then I'm just going to flip it so it'll be like that, right? So absolute value of f is in pink and f is in black. And what we're saying is that, look at the picture here, the sup minus the nth of the pink has to be less than or equal to the sup minus the nth of the black. And that makes sense because when you're looking at the absolute value of f, your numbers have to be closer to each other, right? Your numbers aren't going to be further apart than if you're looking at the original set. So by flipping those negative values, the only thing you've done is possibly bring some nths up. Make sense? And bring some soups down. So you could have brought some soups down, you could have brought some nths up. So the values in the absolute value will be close to each other, closer than the values of the original function. Okay? And so now you prove that fact, okay? Prove this fact right here, and then you apply theorem 32.5. You remember 32.5 was our Cauchy condition. So for every epsilon, there's a partition such that the difference between the upper and the lower sum with respect to that partition is less than epsilon, okay? All right, so I think that's it. We've gone through all of these properties, right? And make sure to read about the monotonic and piecewise monotonic and piecewise continuous functions in Ross. But we went over the broad idea of that briefly in class, how to get from monotonic to piecewise monotonic. You just take your function, as I said before, you take your function and you just break it up into these indicator functions times subsets of that function, right? And so monotonic functions have to be Riemann integrable. Sums and products of Riemann integrable functions have to be Riemann integrable. Constant function is Riemann integrable. Continuous functions are Riemann integrable. Piecewise continuous functions are Riemann integrable. If you have functions that are integrable, they satisfy this ordering property. If f is less than or equal to g, then the integral of f is going to be less than or equal to the integral of g, right? You have this triangle inequality. The absolute value of the integral will be less than or equal to the integral of the absolute value, okay? All right, so as usual, let me know if you have any questions, and I hope to see you soon.